So, gravitational waves have been detected at LIGO, the Laser Interferometer Gravitational Wave Observatory. Wow, that was long. This is located in Louisiana and Washington State. Everywhere, on every social networking website or any online magazine or all the news channels are just booming about these gravitational waves. Everyone just talking about them. But there are many people who don't actually know what these gravitational waves are, and are they actually so important, and is it something to be excited about? Yes, indeed. These are really exciting things. And let's first talk about this man, this genius, Albert Einstein. Then I'm gonna talk about what are these gravitational waves, what do they do, and how did LIGO detect them, and how are they useful or exciting to us. So Albert Einstein predicted these gravitational waves as a comment to his theory of gravity, which is known as the general relativity. So what does this general relativity say? It says that mass or energy, this is a mass or energy, bends or curves the space-time. This is a space-time that is curved beside it, and this space-time, this curved space-time, okay, what's the space-time? Space-time is 3 dimensions of space plus 1 dimension of time. In physics, it's called the marriage between space and time, and it's called a space-time continuum. This is the space-time continuum. And this curved space-time tells mass or energy, how should it move in it. So mass energy bends curved spacetime, and this curved spacetime tells mass here how to move in it. So you can see this mass will eventually fall in it. This theory was in 1915, and Newton's theory of gravity dates back to 1600s. So how did this theory win over Newton's theory of gravity? That happened because of Hubble. The proof of this theory was definitely by Albert Einstein, but the observations made behind this theory are by Hubble after the postulation of theory. So here is the sun, here is an earth, this is kind of an eclipse, and you can see any light reflected from this object is gonna go straight. As we knew back then, light traveled in straight path, so you can see here, but you can see this light wave actually goes like this and it hits the earth. So talking in terms of Newton's gravity and light rays traveling in straight line, this object can never be seen from the earth. But if you consider Einstein's gravity, it will tell that this object can be actually observed by earth, because this light waves goes like this and it bends because of the curvature of space-time over here. And this is what Hubble did observe and proved Einstein's theory to be correct and this theory to be wrong. Not exactly wrong, but kind of in this phenomena, Einstein's theory does triumph over theory of gravity by Newton. Let's talk something more about this curvature of spacetime. Einstein said that this spacetime does not only curve, but this spacetime can do stuff like vibrating and sending ripples, sending ripples. So what do I mean by sending ripples? Imagine this to be a pond, and you have just thrown a stone inside it and you see ripples coming out. That's what I mean by ripples. But in this diagram, these are no stones. These are two neutron stars. What is a neutron star? A neutron star is a dead star, and by a dead star I mean the fuel of the star is completely over, and it no more can generate energy, and it has been through a supernova, and it has been collapsed into itself after that, and finally you form a neutron star, which by the name itself suggests it's made of neutrons. A fun fact about these neutron stars is this is like one step before the star becomes a black hole. Yes, so this neutron star is extremely massive, so it has a really strong gravitational field. So any object which comes in the vicinity of this gravitational field falls in the neutron star, and this neutron star eats up a lot of stuff, and it finally collapses into itself to form a black hole. And this black hole is formed after the neutron star reaches a specific mass, which is called the Chandrasekhar limit. Okay, so that's the thing about neutron stars. Some data about neutron stars. The mass of these stars is 10 to the 30 kg. That is the mass of the sun, and the radius of these stars is just 10 kilometers. So it's like fitting a sun into a radius of 10 kilometers. The actual radius of the sun is 10 to the 5 kilometers. So you can see these are really dense stars, extremely dense stars. These are two neutron stars revolving around each other, and there is a slight possibility that they can collide and collapse into each other, which will be a really energetic phenomena. Such phenomena like the collision of two neutron stars or two neutron stars revolving around it causes gravitational waves. These gravitational waves are the fraction of a size of a proton's diameter, that is extremely tiny, and detecting them is really difficult, as you need extremely sensitive equipments. So uh, what are these gravitational waves again? So these waves are just ripples in space-time created due to extremely high energetic phenomena. These are ripples that will propagate through the space-time, just like a wave. A wave propagates as I'm speaking. The molecules in the air column around me are being vibrated, and because of that you are able to hear me. That's propagation of sound through air. This is the propagation of energy, that is gravity, through the space time. As this is something different. This is not a light wave, this is not a sound wave, this is something of a new wave that we know now. So what is the effect of these waves? The effect is compression and stretching. So let's see it in this way. All the objects we know are embedded in the space-time continuum. Yes, we are embedded in the space-time around us. So it is not the object that compresses or stretches due to these gravitational waves, but the space-time around it which compresses or stretches. So you can see a perfect circle over here, and if a gravitational wave is going in this way, it gets compressed in this direction and it gets stretched in this direction. And if a gravitational wave is going like this, you can see, then this gets stretched in this direction and compressed in this direction. So these are pretty exaggerated pictures. The effect of these gravitational waves on such an object is really small, really difficult to detect. This is an exaggerated diagram just to show what it's like. Okay, so let's see what happened at LIGO. So what happened at LIGO today? Well, not today, it happened pretty long back, but they announced it today. So this is how the setup at LIGO is. So here is a light source, and the light waves goes here, and this is a beam splitter. This beam splitter splits this light wave into the arm 1, and one goes to the arm 2. This arm 1 and arm 2 are 4 kilometers long. This is not a small laboratory experiment, but a big field laboratory experiment. These are long tunnels or tubes, you can say, vacuumized tubes, you can say. So the light waves goes here, hits the mirror. This is an extremely shining mirror. This mirror does not alter the wavelength or the frequency, which is kind of the energy of the wave of this light. It does not alter it at all. So it splits it up, it goes here, it comes back, it happens the same over on this arm too. It goes here, it comes back, and they join together and they become as they were happily. So here you can see what's happening. This is the wave 1 at this point, this is the wave 2 at this point, and together what we know in physics is called interference. This is a constructive interference, as I'm showing you at the moment, and they become as they were earlier. They join together. So you can see here, this is when there's no wave, this is when there's a gravitational wave, this is the gravitational wave. So this arm gets compressed and this arm gets stretched. So because of that, so the same happens. The light wave is going here, it splits up. Now there's something different. Because this distance is small, this reaches here and comes back here before this comes back, because you go here and here, you go here and here. So this reaches here first and this takes a little longer to reach. And as you can see, they are not the same they were. There is some phase difference, what we call here. So this is the wave, this wave, and this is the other wave. So this, the purple wave and the orange wave, they do not match up like this, but instead what's happening is they are forming they are shifted by a phase. So this can only happen when there is this gravitational wave. Everything else in this equipment or the setup is really sensitive, and such things cannot have, or such a thing cannot occur without a gravitational wave. So yes, this is what they detected, and this shift is extremely small. It is extremely small and extremely difficult to detect, but they did it, and that's how we detected a gravitational wave indeed. So how is this gravitational wave important, and why is this big news? So because why is this big news? Because till today we were exploring the universe using electromagnetic waves, that is light. Yeah, so we could see millions of light years away in space by our telescopes, and we were detecting the information over there by electromagnetic waves. But now, because of this huge detection, we have a complete new area in physics, that is the concepts of gravitational waves, and we can use this to explore universe in more elegant and beautiful ways. This also helps us understand how gravity propagates through space and time, and has given us a more concrete base to Einstein's theory of gravity. That's the general relativity. This will help us understand Big Bang even in more detail, and this is how our universe began. As Big Bang, the intensity of gravity waves created during the Big Bang will be tremendous. It's gonna be really tremendous. It's the most energetic bang that happened. That's what created our universe. This will help us to understand how the early universe looked like or behaved. By early universe, I mean a few micro of a nanoseconds. Yes, a micro of a nanoseconds, when there was an exponential expansion according to physicists. After the Big Bang, when everything was opaque. What do I mean by opaque? In the early universe, everything was plasma. There were no atoms, so light never got out of a specific radius or whatever. Um, it just was absorbed and emitted by electrons. There were no atoms, there were just free electrons, which is plasma kind of. So this opened many gates of research, and this is a huge leap for humankind. And hats off to LEGO. This is a really big news, and I hope everyone knows what it is now, and I hope everyone can agree with me that this is a big news. And thank you for watching.